Hi everyone and welcome back to PrepFusion. I'm Anish and today we will start with the lecture 52 of our electrical machines subject. So today we will discuss about the behavior of synchronous generator in different loads. Like in the first lecture of synchronous machines, we discussed about like what kind of load if you are giving, what kind of excitation will be there, right? So exactly we will go through those things in more detail today. Okay, in more detail we will go through that for synchronous generators. Also we'll solve few questions. Also we'll understand like we quickly recap about real and reactive power and why is it important here. Okay, so like few things you already are knowing that I will just quickly go through about the types of load. So if I have a resistive load, like you already know this, that what is the phase difference between the voltage and current. So if voltage is along this reference, what will be the phase of the current also will be in the same phase as the voltage, right? If it is a resistive load, and for a resistive load, what is zero? The reactive power Q is zero. What is not zero? The real power will never be zero, right? Okay. Now remember, for inductive load, if it is not purely inductive, if it is purely inductive, then the power will be zero. But if it is not purely inductive, then the active power will obviously not be zero, because there will be some resistive component and there will be some reactive power. Of course it will consume some reactive power. Okay, so I will write here, if the load is not purely real, it's not purely real, sorry, purely uh, inductive or capacitive, then P will not be equals to 0. Okay, so I will I will have this point as a side note, right? This should not be here, this should be somewhere. Okay, why should I keep it somewhere here, right, as a note? Okay, so here what is the phase difference between voltage and current? So for an inductive load, obviously the current will lag the voltage, as it is not purely inductive. It will not be 90-degree lagging, but somewhat lagging nature there will be between the voltage and current. For a for a capacitive load, the current will lead the voltage. Current will lead the voltage. Okay, that is what will happen for a capacitive load. Okay, so again here, right, power will not be zero, right, and Q also will not be zero. So just a quick overview for a capacitive load. So for a capacitive load, the power factor is called as leading power factor, right? Leading power factor. For an inductive load, it is called as lagging power factor. Okay, and for a resistive load, it is called as unity power factor. Okay, so these are the different power factor. And one more important point is a inductive load will always consume reactive power, correct? So inductive load consumes reactive power, because why will it consume reactive power? Because it has to make the magnetic field, it has to develop the magnetic field. That's why you will see an inductive load always consumes reactive power. Okay, consumes reactive power. What about a Capacitive load. So a capacitive load, what do I keep this one? I'm not getting a space. Okay, so this right should to be somewhere around here, I guess. Yeah. Capacitive load consumes, not consumes, delivers reactive power. So capacitive load has the capacity to deliver reactive power. It will not consume the reactive power. So it can deliver reactive power. Okay, because it does not need to make magnetic flux. It can deliver. It has the capability of delivering. Right. So from here, right, the Q, it can supply Q. This will always consume Q, and this has Q equal to 0. Okay. Few important points. Now the power, all three will always consume power, right? All three will always consume active power. Reactive power depends which one is delivering and supplying. Now if it's a RLC load, right? Here if all of them are RLC load, then what I can comment, is that my XL will be equals to XC. If it's a RLC load, my XL will be greater than XC here for a series, RLC, right? For a series RLC. Otherwise, like things will be different, right? Series RLC I'm talking about. Here as well, if it's a series RLC, I'm not getting enough space. Like overall, although it has bit of inductive nature in it, but overall the capacitive nature will dominate. So if it's a series RLC over here, my XC will be greater than XL. Okay. So that is what will happen over here basically. So I hope you have understood these basic points. Now we will come to the next point. Okay, let's now move on. So like whatever I have discussed, same thing is written over here only, that real power is what, reactive power is what, and what is apparent power. This like just a quick overview. Now summary, purely resistive, active power will always be 1 0, but for reactive power it will be 0. And here inductive, it will consume reactive power, like induction motors, transformers, all these will consume. So not all motors, right? Not all motors, induction motors always will consume reactive power, but sometimes, right, synchronous motors can consume or deliver the reactive power. It depends on the type of excitation that obviously we will discuss, right? So capacitive loads consumes real power, delivers reactive power. Okay, so now let's come to motor. So when I say a motor will always consume real power, no matter what, it will always consume real power. Why it will always consume real power? Because it has to provide some mechanical output. If it has to provide some mechanical output, like rotating this whatever object, so it has to do some real work, right? Like your fan, all those things. It will always consume the active power no matter what. So there will be some resistive component here, no matter what. But our motor can behave, synchronous motor can behave as a capacitive load or a inductive load depending on the excitation. Okay, we will discuss how we can change the excitation in the next lectures, but for now we say that our motor is operating in lagging power factor when the motor draws the reactive power. So motor will consume the reactive power. If the motor is consuming the reactive power, if the reactive power is going into the motor, then we say it is operating in lagging power factor. We say the motor supplies, when the motor is supplying the reactive power, it is possible. In case of synchronous motors, it is possible, not for induction motors. Okay, yeah, for synchronous motor it is possible. For induction motor, it can only consume reactive power, cannot deliver reactive power. So here if it delivers reactive power, then it is known to operate in leading power factor. And what do you know about leading power factor? Leading power factor basically means the load is behaving like a capacitive load. Unity power factor, when there is no reactive power flow, only real power is consumed, then it is told to be as resistive load, unity power factor. Okay, very simple to understand. So there is no Q, no incoming Q, no outgoing Q. Q is 0 basically. Okay, I hope you have understood this point. So what will be the phase difference between the voltage and current here? As the it is a lagging, so current will lag the voltage here as it is leading. So current will lead, and here basically both of them are in same phase. Okay, so if both of them are in same phase, both of them will operate in unity power factor. Okay, so uh, synchronous generators, primary source of generators. What about generators? Now for generators, right, it's very different, because one thing you have to understand, that your motor always behaves as a load. Okay, motor always behaves as a load, and mostly whenever we say power factor, mostly we say the power factor with respect to load. So very important point, power factor mostly is said with respect to load. Now this point, right, is very important. This point is very important. Why this point is very important? Because if you see here that I have synchronous generators, right? So primary source of electrical power generation. So real power is always delivered to the load. Okay, real power is always delivered to the load. That I already know. So generator always will deliver the real power. That much is sufficient. Now the point is, if I say the generator is operating in lagging power factor load, what does it mean? If the generator is operating in lagging power factor load, that means the load is consuming reactive power, and generator someone has to deliver the reactive power, right? So generator will deliver the reactive power. So when I say generator is operating in lagging power factor, okay, if unless and until it is specified, it means they are talking about the load only. That basically means that generator will supply the reactive power. Okay, generator is operating in lagging reactive power, that means the load is lagging, that means the load will consume the reactive power, that means generator will deliver the reactive power. Very important thing, please keep this in your mind. Now generator is operating in leading reactive power. Leading reactive power means load is capacitive, that means load will deliver the reactive power and generator will consume the reactive power. Okay, so generator will consume the reactive power, so generator absorbs the or consumes the reactive power. Unity power factor, there is no like power reactive power transfer. Okay, so power factor is always specified with respect to loads perspective, not with respect to source perspective, unless and until specified. Sometimes in power electronics we ask source power factor, but unless and until specified, mostly it is specified with respect to loads perspective, because I know the power factor of load, right? I will not know what power factor generator is operating, because generator will operate in that power factor whatever you want it to. If you want your load to consume reactive power, so generator will supply the reactive power. Okay, so always mostly we specify our power factor with respect to load unless and until specified. So in power factor, there in power electronics, there is a term known as source power factor, but that is like a very far-fetched topic. I don't want to discuss about that now. Okay, so but in machines you don't have to worry about source power factor. Okay, in power systems as well you don't have to worry about source power factor. Just in power electronics you have to worry about that. Okay, so yeah, for example, if a load is said to be operating in 0.8 power factor lagging, that means the source generator delivers real power as well as the positive reactive power. Generator will deliver both the real power and the reactive power. Okay, so this was a summary about the synchronous motor and generator. Now what about for a synchronous motor? For a what about for an induction motor? So induction motor, right, it is a induction machine is a singly excited machine, right? Singly excited machine, that means we don't have the air gap flux, because in synchronous motor it is a doubly excited, so already the field poles we give it DC supply to get the air gap flux. So someone, this is induction machines, needs to someone needs to generate the air gap flux, be it for generator, like we can use this induction machine for generator or motor, right? So to generate this air gap flux, what do you need? You need reactive power. So induction machines will always consume reactive power. Induction machines will always consume reactive power no matter what. Okay, so whether it be it generator or motor. Now if it is working as a generator, right, generator, what do you know, will deliver the real power, deliver real power, and a motor always consumes real power, right? So summary, bottom line for induction machines is that if it's a induction machine, right, it will consume reactive power no matter what. If it is induction motor, it will consume reactive power and real power. If it is operating as induction generator, it will consume reactive power and deliver the real power. So same thing is written over here. It is a singly excited machine, meaning that only stator is directly connected to AC source. To produce a rotating magnetic field, it draws magnetizing current no matter what, right, from the supply. This current is required to magnetize the core and establish working flux. The magnetizing current lags the voltage, thus the induction motor always, no matter what, will operate in lagging power factor. Induction motor will always operate in lagging power factor no matter what. Okay, it will consume real power if it is operating as a motor. Okay, if it is operating as a motor, and it will consume reactive power. Okay, I'm talking about only motor. So as a motor, it will behave as a capacitive load, right? It will be, sorry, inductive load. It will behave as a inductive load. Okay, so sometimes what happens is, like, one thing, if you understand it, right, uh, that our current is what? Current is a combination of real component plus the imaginary component, right? I imaginary. Now I imaginary is basically I inductive here. So what we can do, we can add few capacitors so that those capacitors will supply the required reactive power. So what will happen? Overall, this inductive current will reduce, that was taken from the supply, right, will reduce. If this current reduces, the magnitude of I reduces, then the magnitude of I square R reduces, right? So this I will discuss in power systems, not that important, but bottom line is I want to reduce the magnitude of I so that the losses in the line has been reduced, so that our system is operating at better efficiency. So in those kind of cases, we use this power factor correction capacitors, which are installed near motor terminals, to basically help the motors deliver the reactive power that is required. I don't deliver it through the supply, I deliver it through a external capacitor. Of course it will have its losses, we have to add capacitors, that will have its cost associated, but this will save us efficiency. Okay, what about generator? So generator again is a asynchronous generator, it will not rotate in synchronous speed, basically it will not deliver in same frequency. But here what will happen, uh, just like a motor, it is singly excited. So in this case again, it will consume it will require the magnetizing current. So still it will consume the reactive power, but it will deliver the active power. Here it was consuming the active power, here the generator will deliver the active power. That is the only difference over here. Okay, I hope you have understood. So simply, if I connect a lagging power factor load here, this will not work. Okay, so if I connect here lagging power factor load, this will not work. Only, so induction generator will work in capacitive loads. Okay, very key point. In, so here the same thing is written. Because of this, the induction generator always behaves like an inductive load. It operates in leading power factor, right? So whenever generator absorbs reactive power, it is said to be, it is operating in leading power factor. Basically the load must be in leading power factor. Basically the load must be capacitive in nature for proper operation. So this is the most important point over here. I hope you have understood. This is the most important point, that load must be capacitive in nature, right? So that's why you don't see induction generator everywhere else, because mostly our loads are inductive, right? And if my loads are inductive and if I am using an induction generator, it will simply not work, because it also needs a reactive power. So simply it will not work. That is the problem over here. Okay. So I hope you have understood this point. So what we do with the induction generator, right, we connect a auxiliary generator or we connect few capacitive loads that will supply the required reactive power, right? Since in the induction generator cannot self excite, it must receive reactive power from an external source, either from the electric grid via synchronous generators or a capacitive banks, okay, like this. Okay, so yeah, you can go through this same thing, whatever I'm explaining, they have explained it over here. So this is basically the isolated mode, when basically we are operating our generator in off grid. Off grid meaning that, like, I am not connecting it to a grid which has a constant terminal potential, right? I will discuss about this, what does grid means, okay, what does off grid means, just in the next few slides, don't worry. Okay, so this kind of examples are generally used in isolated mode, like either we can use it in grid connected or isolated. When off grid, we can use it as a capacitor bank, because like someone needs to supply this reactive power to this induction generator, right? So the capacitor can deliver the reactive power. Okay, so that is how we can use it in the isolated modes. So that's why you can see that induction generators are widely used in wind energy. Why are they used in wind energy? Because if you remember, right, induction generator or induction motor, the speed varies with respect to the what, with respect to the load, correct? But still the supply frequency is constant, 50 hertz, right? So we want a generator that can have constant frequency, that can give constant frequency even if I vary the speed. So accordingly the slip will change, correct? So induction generator has that characteristics, because in wind turbines, what happens is the speed in wind turbines, speed is not constant. Sometimes more wind will be there, then speed will be higher. Sometimes less wind is there, speed will be lower. So even if the speed is varying, even if the speed is a variable, n is variable, right, frequency will still be constant. This can only be possible in induction generator. Don't worry, don't go into the theoretical things here, just intuitively try to understand this. This much only is required for you to understand, okay, nothing else. Because in synchronous generator, if you know that frequency is directly proportional to speed, right, ns equals to 120 f by p. So that's why we don't prefer this, right? We don't prefer synchronous generator in wind turbines. Okay, very key point to understand here. So this is the summary basically, that difference between induction motor and generator. Induction motor, we convert electrical to mechanical. Generator, the opposite. Real power consumed from the supply, it will be delivered to the grid or the load. Okay, reactive power, it is always drawn from the supply. Okay, always reactive power will be drawn from the supply. It does not matter if it's a motor or generator, we will always draw the reactive power. Okay, so excitation, both of them are singly excited. Power factor will be lagging. It will be leading from the system's perspective, because we have to connect a leading load, right? Then only the load can deliver a reactive power to the induction generator. Okay, so it will be operated above synchronous speed for the generator, below synchronous speed for the motor. Okay, common use will be fans, pumps, conveyors, and in case of generator, it will be used in wind turbines. Now let's come into a bit of basic topic about the excitation. Okay, so one very basic thing we know, right, very basic thing we know, that in synchronous generator, right, and in induction machines as well, that we have this flux, and that is a time varying flux. Due to that, a voltage will be induced. What is the value of the voltage? So value of the resultant voltage, if you remember, it was equals to 4.44, or I can write it like this, root 2 into pi into f into phi into per phase number of turns, right? And it was the flux per pole, right? This was the formula, correct? This is roughly equals to my V, right, the terminal voltage. Roughly I can assume, I can neglect the leakage reactance drop and the armature resistance drop. If I neglect it, roughly it will be equals to V. Okay, so now from here what can I identify? I can identify that the flux, right, again same equation, flux per pole is proportional to V by F. So basically it means if I increase the flux per pole, right, voltage also will increase. So this basically means the excitation, basically voltage is equals to excitation only, so my excitation also will increase. I mean the induced EMF also will increase, right? All of it depends on the flux per pole, right? If I increase the flux, if I give more amount of flux, the excitation voltage will be higher if the frequency is constant. Assumption is we are operating in constant frequency. Why we are operating in constant frequency? Because I am rotating the generator in a constant speed. Okay, I hope that is sorted. Okay, so if the frequency is constant, then your flux, if I increase the flux per pole, your voltage will be automatically increased. Now let's understand this other way around. If I tell you that I want a constant voltage, basically I want a constant voltage, this I need a constant, right? If this I need constant, that means I need this flux to be constant, correct? That means I need the flux to be constant. If I need the flux to be constant, that means like whatever flux that the DC supply is able to generate on the field poles, right, rotor. So basically field flux should remain constant. Now one thing, if you remember, we had drawn for three kind of loads, right? We had drawn for unity power factor, like I will not do it again, for lagging power factor, for leading power factor, and for lagging power factor, correct? Lead and lag. So in this three, if you remember, that in unity power factor, the field flux did not used to get reduced, right? Whatever field flux was there, that was there, just it was cross magnetizing. So in unity power factor, the effect was cross magnetizing. In leading power factor, if you remember, the effect was magnetizing. Armature reaction, basically I am talking about the armature reaction, right? Armature reaction. Here it was magnetizing, here it was demagnetizing. So these three were the cases. You can go and just see your notes. Okay, you will see these three were the conclusions. So let's discuss something similar. So we have this condition here. We have rotor winding, stator winding. It's a doubly excited machine. I am rotating the rotor with providing a DC supply. Now I want to check that. Let's assume that initially my phi f is 40 milliweber. Okay, and phi a, right? It depends whether what kind of current it is, whether it is lagging, leading, that how much will it reduce my field flux, that I want to know. Okay, so I know that at unity power factor my phi f will not change. Okay, so at same thing is written over here, at unity power factor the armature reaction, right, will be zero along the direction. This is actually, there will be some armature flux that will be there, but I am talking about the armature flux parallel to 5. Okay, either parallel or anti-parallel. Okay, I'm not talking about armature flux other way, because of course if there is current there will be armature flux, that is for sure, but I am only talking about armature flux along the direction. So here, right, in this case the armature reaction is cross magnetizing. This is already concluded in the previous lectures, right? It distorts the main field flux without increasing or decreasing overall the flux magnitude. It will distort it, right? Overall the magnitude will not change much. Overall the magnitude will not change, it will distort it, that's for sure. So this kind of excitation, right, when the power factor is unity, is actually called as normal excitation. Why is this called normal excitation? I will explain it to you, okay, just in a second. So when the generator is connected to a resistive load or a unity power factor load, it is said to be operating in normal excitation. Okay, just I will explain this synchronous machine operating at unity power factor ideal where reactive power compensation is not required. I will explain just in a second. I will explain this. Okay, so now let's come to the next part, that is leading. For leading, what I told you, leading, the effect was magnetizing. So even like basically this, right, this voltage depends on what? ER. This voltage depends on ER, and ER is depending on the phi r flux, right? This flux basically, correct? So if I see in the second case for a capacitive load, what happens is, even though if the field flux is 30 milliweber, if let's say due to armature reaction the armature flux is 10 milliweber, both of them will be additive in nature. Why? Because it is magnetizing. Okay, already I have been explained. So overall the resultant flux along the field flux direction will be 40 milliweber. So for less amount of excitation in the field winding, less excitation in the field winding, I am getting the same resultant flux, that is same resultant voltage, same voltage at the output. So that's why this is known as under excitation. I don't need to excite my generator that high. Without even exciting my generator lower value, I am able to produce enough flux. I am able to produce enough flux. Okay. Here, let's come to the overexcitation. Overexcitation is when the armature reaction is demagnetizing. Okay, it is demagnetizing. That means if even if I have 50 milliweber of field excitation, field flux, I will not be able to get that at the resultant. Resultant will be subtraction of the armature field flux and the field flux, right? So basically it will be 40 milliweber. So overall I will have 40 milliweber. So I hope you have understood this point, that even with higher excitation, higher field flux, I am only able to produce 40 milliweber. That means we have to over excite our machine, then only I will be able to get to the same voltage level Vt. Okay. So now I hope it is clear that to get the same amount of Vt, to get same amount of terminal voltage Vt, the excitation may differ. Okay, excitation may differ. So in this case, the load was to the generator, it was a simple capacitor, right, capacitive load, and here it is simply inductive load. Okay. Now one more key point, like here the summary table is given. If it is like normal excitation, that means I don't have to do anything extra, because the armature flux will be cross magnetizing, it will not affect the main field flux. So I don't have to provide any extra excitation or lower excitation to get the same amount of voltage. So all these are at constant voltage output, that is constant Vt. Okay. Now if the load is leading, then I don't need to excite it that high. Under excitation will work. That's why the name under excited. For lagging load, I have to over excite, produce more amount of flux, right? Then only then only overall I will be able to get a constant Vt. Now the same thing I can say to you for a for the other way around. What is the other way around? Other way around is that if my flux is constant and power factor is constant, right? If my flux is constant and power factor is constant, so what do I want to say? Yeah, sorry, not flux constant, sorry. If my power factor is constant, that is cos phi is constant, right? Cos phi is constant. Now what is my flux dependent on? Flux is dependent, flux per pole is dependent flux per pole is dependent on Vt upon F, right? Or I can say E upon F, right? So the higher excitation I provide, more excitation, higher the induced EMF, depending whether the power factor is constant. So this is also another key point to understand, right? More excitation, more induced EMF, given that the power factor of the load is constant. Okay, so these two conclusions are very important for you to understand. Okay, now let's try to understand what does infinite bus means. Although I've explained a bit, but I have not totally gone into that exactly what does infinite bus means. So I will exactly explain what does infinite bus means. Okay, so the term infinite bus refers to a very large power system with essentially constant voltage and frequency regardless of the amount of power it supplies or receives. So basically it is just like a voltage source, just like a voltage source. Assume it like a voltage, ideal voltage source. Okay, but we call it a infinite bus because a voltage source is just a simple small thing, right? Bus is like a huge, all whatever supply you are receiving, right, that is coming from the bus. It's like a huge power station, it's coming from that. So it's a like big thing, it's not a very small thing. That's why we cannot say it's like a ideal voltage. So but you can get the analogy that it will be similar to a ideal voltage source. Okay, so yeah, that is the case over here. That is the case over here. I hope you have understood this point. Now what I can comment, is that now what are the characteristics of a bus? Terminal voltage will be constant. So this is the symbol of a bus where Vt will be constant and frequency also will be constant. Constant frequency, constant terminal voltage, and unlimited power source or sink. So I can provide unlimited amount of power to it. Basically it can absorb unlimited amount of power or can deliver unlimited amount of power depending on what kind of load is connected, right? Same like a ideal voltage source. Okay, so why is it important? Understanding the infinite bus concept simplifies the analysis of operator, because sorry, alternator, right? Because alternator will operate in a power system, right? And you have to have a terminating point, otherwise how will you be able to analyze the alternator? So for that reason, this understanding this infinite bus is very important. Now let's come to our alternator fundamental equation, right? So if I am connecting a alternator to a infinite bus, right, with synchronous impedance Zs, right, this will be Vt, this will be E, developed voltage, so and this will be the current. I angle theta. Okay, so basically I can write this equation, the same equation that they have written over here, Vt plus Vt angle 0 because it is the reference, plus Ia angle theta plus Ra plus Jxs. Okay, same thing it is written over here. So the term IARA represents the voltage drop across the alternator's internal impedance Zs, right? Now if I neglect the RA, then the analysis will become much simpler. EF will be equals to Vt plus J IAXS. Now this equation, right, is very important actually. We'll analyze this equation, okay, because generally RA will be much lower. You will see in the questions as well than XS, right, magnitude. So you can neglect the RA. Now there can be two kinds of analysis. So first analysis is the, like I want to analyze this equation. First analysis will be fixed excitation and varying the terminal voltage, right? If I'm varying the terminal voltage and then I'm just fixing the excitation, how will the current vary? All those things will vary. That is what we want to understand, right? How will the terminal voltage vary depending on the current if the excitation is fixed? So Vt as a function of Ia. That is what we want to see. And here, right, what we do, we have fixed terminal voltage and we want to plot EF as a function of Ia. And this is the generally what we study, right? Generally this is the main one. Why? Because I already told you that generally our terminal voltage is fixed because it is coming from infinite bus. But this can be extremely helpful if you want to do the analysis of a isolated system. Isolated system just like this, right here. Just like this, we did the analysis here, isolated system, same. Okay, because there, right, you decide the terminal voltage, not the infinite grid. You decide the terminal voltage. That's why it is written here isolated operation. So now let's first discuss if it is isolated operation. That basically means my EF is fixed. So what is my IA basically? That is what I want to know. So let's do the analysis at different power factors. Okay, so let's first do at 0 power factor leading. If it is 0 power factor leading, that means basically my current IA will be IA angle plus 90 because it will lead the voltage, terminal voltage. It will lead the terminal voltage. So basically what I can say that this E, right, will be EF equals to Vt. This is what J is. What J is basically 1 angle plus 90, and again I have Ia whose this is magnitude of Ia into plus 90. Ia will vary, magnitude of Ia will be varied, but power factor is constant. So one more thing, like we will vary Ia by varying, like power factor also will be varied, but different curves will be obtained. So if this is the case into xs, so I observe this is like plus 180. Plus 180 basically means minus 1. So this will be Vt minus Ia xs. So EF is Vt minus Ia xs. So here, right, what is my Vt? Vt is simply equals to EF plus Ia xs. So basically the graph for your Vt will be plus Ixs. So if it's a leading load, your Vt basically will increase with current. Okay, your Vt basically will increase with current, right? So here what will happen, how the graph will look, how will the graph look? So graph will look somewhat like this, that it's a straight line. What is variable here? Ia is variable, xs is constant, ef is constant, everything else is constant, right? Only your Ia is variable. So here, if this is the Ia, I am varying the magnitude of Ia, right? And this is my Vt. So at when Ia is 0, this graph will be only for the 0 power factor. When Ia is 0, it is equals to Ef, right? So I will be somewhere around here, Ef. If I keep on increasing Ia, what happens? The voltage, terminal voltage also increases. So the terminal voltage actually is higher than the field excitation voltage at 0 power factor. Very important point to understand. At 0 power factor leading, the terminal voltage will be higher than the field excitation voltage. Okay, if I keep on increasing the armature current. What about 0 power factor lagging? 0 power factor lagging, if I see this equation, right, 0 power factor lagging, what will be the current? Current Ia equals to Ia equals to IA angle minus 90. IA equals to IA angle minus 90, right? So what will be the this time VT now? So VT again is equals to EF minus J IA XS, right? So this is minus 90, this also is minus J is minus 90 only, right? So minus 180, minus 180 is again minus 1. So this will be basically EF minus IAXS. If you see in the previous case, it was plus IAXS. So this time with increase in current, the voltage will reduce. So for a lagging load, this, what is the slope of this? Slope of this will be plus XS. And for a lagging load, it will reduce to here. What is this point? Where the voltage is 0. When VT is 0, what is the value of the IA? IA is EF by XS. That is also known as the short circuit current. Okay, EF by XS, also known as the short circuit current. Okay, so this slope will be what? This slope will be minus XS. Okay, so this was the analysis for a zero power factor, right? Now what will happen for a unity power factor? Let us discuss for unity power factor. For a unity power factor, your IA current will not have any angle, right? IA and VT will be in the same phase. This will be IA angle 0. Okay, this will be IA angle 0. So VT is equals to EF minus J into IA is IA angle 0 only into XS, right? So what will be the VT basically? How can I draw the VT? Right? How can I draw the VT? So this one will be very interesting. You can either draw the phasor, or you can understand it in a different manner as well. That your VT, right? Your magnitude of VT will be what? Magnitude, if I want to compare the magnitude of VT, right? Magnitude of VT will be EF square plus IA XS whole square. It is like, this is constant. This is constant. So it is basically proportional to IA whole squared. Okay. So kind of the nature will be parabolic in nature. Okay, but I will use the phasor diagram. Okay. So if I use a phasor diagram, so let us, like, we have to assume few points. Let us assume that my EF is constant. So EF is here. EF is here. Let us assume that EF is here. Okay. Now, what else can I do? Now, let us assume that IA is here, right? IA is here. So if IA is here, so will be my VT, right? Because IA and VT are in the same phase. Now, how can I write my VT in terms of IA? So IA is here. Okay, IA is here and EF is here. So I know VT will be along this line only. VT has to be along this line, no matter what, right? So VT has to be along this line because it is a unity power factor. So VT and IA must be parallel to each other. It's unity power factor, right? So VT will be somewhere here. I'm sure. But exactly what is the length of VT? How can I comment? How can I comment the length of VT? So length of VT will be commented by this equation. So EF I have to subtract this J into IXS. So J into IA will be this, right? J into IA will be this, but I have to subtract. If I have to subtract, I have to draw the vector in opposite direction from this point. So I will copy this IA, and I will rotate this by minus 90 because it is minus j, right? If you see here, it is minus j. So I have to rotate it by minus 90. So minus 90 will be here. Okay. Now if I connect the head and tail, now this drop, right? This drop has to intersect somewhere along this line. Okay, it has to, no matter what, it has to intersect. So it's intersecting here. So this will be my VT basically. Now if I, so how do I draw it? This is a VT. So VT is this, right? It's almost similar to IA, but VT is something else. So this is my VT. Okay, this is my VT, and this is the angle delta. Okay, now let me change IA because IA is very well, right? IA is very well. I can make my IA here. That is also totally fine. How do I? Okay, yeah, I can make my IA here, right, and make it. Let me make it a bit small. Okay, IA. Let's assume IA is here. Now, if IA is here, again the same thing, right? Again, I will. Let me recolor this. Otherwise, you will get confused. And if I add the drop here, right? And again, one thing that my VT should lie along this. VT should lie along this because VT and IA are in the same phase. It is a unity power factor, right? So this I will again rotate by minus 90, and then again I will touch it here. Touch with this, right? Exactly somewhere. It is not exactly 90. Forgive me for that, but I hope you understand the point. So my VT will be here. VT will be here. This will be VT. So basically what is happening? So basically it will follow a locus of a semicircle, right? Your VT, right? If your EF is here, okay, when IA is along EF, what will happen? Same drop, VT will be here only, right? VT will be somewhere here, right? Okay, so your VT will be just like a semicircle, okay? If you keep on plotting your VT with respect to IA, it will be just like a semicircle. Although this is not perfect here, but it will be semicircle. So in the graph, basically for a unity power factor load, when IA is 0, EF is, sorry, VT is EF only, right? When IA is 0, VT is EF only. When IA is, okay, this time it will not touch over here. It will not come over here. When IA equals to, EF by XS, right? Then my VT magnitude will be root 2 EF, right? It will be higher actually. So VT will not go to 0 actually. VT will not go to 0. Okay. So VT will be, it will be somewhere around here. It will be root 2 into EF. So actually the graph would look somewhat like this. Okay. Not perfect though. Just okay. So right, this is actually more steeper. This is more steeper actually. This should be more steeper. This also should be more steeper. That is, this is fine, I guess. So basically, okay, all this is MS. Like I have a good figure drawn. Don't worry about it. So you're right. Your unity power factor will be somewhat like this. So here it will be somewhat higher. If I am just plotting the magnitude, it will be somewhat higher than EF. Okay, so it will be 1.414 EF. Okay, in the same current, it will be higher. Okay, if I keep on increasing IA, your VT magnitude will only keep on increasing, right? Because here I have J, so it is like a orthogonal component. So this, right, VT magnitude will keep on increasing, but will not go beyond this point. So this one, right, will be a semicircle. Remember it. This will be unity power factor will be a semicircle, exact semicircle. Okay. Why it will be semicircle? Because why it will be semicircle, I will explain you. This is your VT, right? So if I write this, what is the magnitude of VT? Magnitude of VT is under root EF square plus IA XS whole square. Correct? So now if I want to write if I am squaring both sides, so Vt square, magnitude of Vt square equals to EF square plus IA square XS square. Okay, so so if I am able to, okay, this is actually not exact, it should be a semicircle only. How is it? Okay, minus this, okay, G plus this, right, square it. This, so EF is constant, it is Vt square minus, okay, Vt square equals to this. Okay, it is actually exactly not a semicircle, so it's like a y square equals to C, EF is constant, C plus this x square into some C1 plus C2, right? Okay, so it's like y square minus x square C2 equals to C1. So it is exactly not, it is like a hyperbola, it is like a rectangular hyperbola, sorry, it will be a rectangular hyperbola. I also have forgotten. I will just quickly check the equation, right? I think it's y square minus x square only. Y square minus x square is rectangular hyperbola, if I remember it correctly. I will just quickly check, right? Minus x square. I don't want to mess up here. It's a, uh, it's a, they are not telling me what kind of graph is this. Graph name. Just quickly check it. It should be, yeah, hyperbola. Yeah, it is hyperbola. Yes, correct. So it is basically, okay, but here, right, the coefficient are not 1. If the coefficient is not 1, then what will happen? Will it be a ellipse or something? Huh? Okay, it is a, okay, hyperbola. It is a hyperbola only. Okay, it will be a hyperbola. It will be a hyperbola. So it is not a circle actually. It is a not rectangular hyperbola. It is a hyperbola. Okay, general hyperbola. So I was wrong here. It will not be a semicircle. This will be a hyperbola. Okay, sorry about that. Here also this will not be a semicircle. This will be a hyperbola. Okay, no one will explain you this, right? Trust me, no one. Everyone will say circle. I also, because in the book it is written there circle, but maybe I'm doing something wrong. You guys can do this, right? According to me, it should be hyperbola only. According to me, it should be hyperbola only. Okay, so you guys can let me know, but according to me, it should be hyperbola. Okay, so you will get a hyperbola for a unity power factor, right? So the graph will be somewhat like this. For a leading power factor, the graph, like that exercise I'm leaving it to you, the graph will be what? Graph will be above this, right? Leading means I will go more higher, so graph will be somewhere here, leading power factor. And for lagging power factor, graph will be below the unity power factor, it will be somewhere here. Here, this will be the lag, this will be the lead. Okay, so yeah, that is a graph, basically that is a summary. So I just wanted to mention the case one. We have just done the case one where the EF is fixed and VT is varying. I'm seeing the changes in the VT with respect to IA and the power factor. Okay, so as I go from lagging power factor to leading power factor, for the same load current, the amount of terminal voltage is increased. Can you tell me why is the reason? The reason might just be that here it is overexcited. So for the same overexcitation, I do not need that additional armature flux, right? So whatever armature flux is there, that is aiding, so automatically the EF is higher. Okay, so it is overexcited and underexcited. I hope you have understood this point. So here it is overexcited and underexcited. Now remember, whatever we are discussing, this overexcited, underexcited, all these things were with respect to a synchronous generator. Remember, synchronous generator. For motor, it will be just the opposite. Okay, I will discuss about motor as well, but for motor it will be just the opposite. Okay, remember, this is very important point. Okay, so yeah, that's basically it. Same thing, right? If no load condition, If it is at no load, right, then Vt and Ef will be along the same direction, right? Like basically Vt will be equals to Ef, right? Vt will be equals to Ef. If Ia is 0, Vt is equals to Ef, correct? Zero power factor, lagging basically means your Vt will be downwards. Vt will be lower than Ef, and for leading Vt will be higher than Ef, okay? But in the same direction, because they will not have any phase difference. There will be linear relationship, right? Either linearly decreasing or increasing. Linear relationship, okay? Okay. And if it is unity power factor, right, so Vt and Ia will be in the same phase. Basically my Ef I can subtract, right? So if it is unity power factor, it will be a hyperbola. Okay, we have already done this, right? If it is unity power factor, from here we have done this, right? If it is unity power factor, right, I was just reducing the voltage, like Ia is in this direction, so in the same direction Vt will be there, right? I know that. I subtracted this drop, whatever this drop, minus j, and then I got my Vt, okay? And the equation will be a hyperbola. Okay, so for any kind of load, this equation, like this we already had derived previously, right? This magnitude of E formula. So from here you can also understand that how the Vt is with respect to E and Ia, right? This we derived in case of lagging and leading load. If you remember, for a leading load, this was the equation. For a lagging load, this was the equation, right? I hope you remember, right? All these things we have derived previously. Okay. So for a any general load, okay, this graph is kind of wrong here, right? Because Ef by excess current will not always produce me zero amount of voltage. Graph is kind of wrong, okay? So correct graph will be somewhat like this, okay? This will be the correct graph. So I will just correct it. I have to correct it, right? This is not like according to me. I also have seen the books, right? Then I forgot to do this by myself. That's the mistake. I should have done it by myself. Okay, I will just redraw the graph. Okay, so as I increase my power factor from lagging to leading, what will happen? The voltage for the same amount of current will increase, right? So let me draw for 0.8. Okay, this curve is not, I'm not able to draw a curve. Okay, let me draw it like this. So this will be here, this will be much higher. Okay, yeah. Okay, this is okay. Let me just extend this as well. Let me keep this behind. Yeah, okay. So this was for 0.8 lead, okay, and I can extend this till here. Okay, and let me draw a graph here as well. This is Ef, and let me draw another line here. Let me rotate this by minus 90. Let me keep it here. Let me say this line is 1.4. EF. Okay, 1.414 EF. So why is this point important? Because at this right same value of IA, the VT magnitude was 1.414 of EF, right, root 2 times EF. So for unity power factor, what will happen? For unity power factor, it will be hyperbola obviously, right? It will be hyperbola. For unity power factor, the value will be somewhat like this. Okay, again I have to draw a curve only, right? Draw a curve only. This time it will be exactly here, here, and the color will be green. That's it. So this is the graph for a unity power factor, although it does not look like hyperbola, but just you have to trust me on that, right? So it is a hyperbola. Okay. Okay. So now for lagging, right? For lagging it is okay. For lagging it will be lower than 0.144. Okay, what is happening? This graph is different. Cannot, okay, it's like a circle only. Oh, okay. For lag this will be here, and zero power factor lag will be here, right? So now I hope the graphs are clear how it is. Remember, this graph is for what? This graph, like whenever you see VT, right, VT is varying with IA, that means basically your excitation will be constant. So your remember in this case your EF is constant, and trust me, this graph is not there in any book, okay? Because in the books also it is wrong, according to me at least, okay? What I am able to see, according to me the books kind of are wrong, okay? So this is the graph. Now let's do a very basic question. Let's do a very basic question, right? If I am giving you three graphs, and please don't look at the previous graphs, okay? Try to answer this right now itself, that I have these three graphs, right, these three curves, and synchronous generator running with constant excitation is constant. As the load this here as the load current changes, load current I am varying, which of the curves correspond to lagging, leading, and unity power factor operation, right? So one more point I will write over here, that let me write this point, that let me mark out this point, right? Let me mark out this point as this is basically the short circuit current EF by XS, okay? And let me mark out this point one point. Four 414 EF, okay? So it will be 1.414 EF. That's it basically. So now can you tell me which one will be the unity power factor? It's very simple, right? So when the voltage is higher than the excitation, that means it has to be a leading power factor. So the curve one has to be leading power factor. As my magnitude of VT is higher than magnitude of EF, and the curve 3 will be a lagging power factor. As I can see, the magnitude of VT is lower than magnitude of EF, that means it is lagging power factor. Remember, all these I am discussing for synchronous generator. For motor it will just be opposite. So these are for synchronous generator, so don't remember it, right? Just write down the equation. What is the equation? VT is equals to EF minus J IA XS, right? So just put the values. You put the values. You assume the extreme case. Extreme case is what? Zero power factor. Zero power factor lead effect assume, that means my current will be what? Plus 90. If current is plus 90, right, then it is J into IA, so JJ becomes minus 1 becomes plus. So basically I am adding with the excitation voltage, right? So voltage will increase. So here this is the case. So this will be the curve one, basically leading power factor. Same you do for the lagging, same you will see. And remember, this is for synchronous generator. Okay, and obviously if you see at this short circuit current, the voltage is 1.414. That means the second curve will be unity power factor. Okay, so this will be the answer. Okay, very elegant and simple question, but trust me, if in gate this simple question comes, 90% students will not be able to solve it. Like, did I require any knowledge of synchronous generator here? Okay, no, simple circuits. But even if this question come, no, like 90% of the students will be failing to solve it, because what they do, they just remember the formulae. Okay, so yeah, remembering formulae is important, but understanding the concept is also very important. So basically, right, this is called as the external characteristics. Okay, whatever we have been plotting. So the two cases we discussed, right? Two cases, this case 1 and case 2. So first case is actually known as the external characteristics. Why is it called as the external characteristics? It is called as the external characteristics because we are comparing we are comparing external voltage of the generator, that is Vt is external, right, with respect to load current, right? And in fixed terminal voltage, that means we are comparing the internal voltage, that is Ef, hence it is called as internal characteristics. So it is Ef as a function of load current Ia. Okay, now one more thing, few guys, like if they have seen the book PS Bhimra, right, their graphs are given, okay, but kind of I think they are not explained properly. So in this graph, right, actually, okay, this will not be a semicircle, right, this will be something else, this will not be exactly a semicircle. Okay, I cannot delete it. Okay, I have to delete it, otherwise you will be confused. Okay, so the ultimate thing is that this graph, right, can be plotted in per unit. So one more thing is, when will I reach here? When my current is Ef by Xs, that is a short circuit current. That current, at that current, what is the voltage? Can you tell me what is the voltage in case of a zero power factor leading load? So if I just come back to this equation, right? Come back to this equation for the leading power factor load where we are deriving it. This was the equation, right? So what is the value of Vt when Ia equals to Ia is equals to Ef by Xs. Okay, Ef by Xs. So Vt is equals to Ef plus Ef divided by Xs. So it is basically 2 times Ef, right? It becomes, Vt becomes 2 times Ef. So basically at this current, short circuit current, the terminal voltage for leading zero power factor will be 2 Ef. Now one more thing what they do is they actually draw this in per unit. So please don't get scared. Please don't get scared if they are drawing this graph in per unit. Okay, don't get scared. Per unit basically means I'm dividing by the rated current. Okay, so let's assume that I have a current I rated, right, and let's assume that I rated is less than Ef by Xs. So like short circuit current generally will be very high. Okay, so I will assume that rated current will be less than the short circuit current, that is when the terminals are shorted. Also, V rated, VT rated, right? Let me assume VT rated. Don't worry, all this will be given to you, will be EF. Okay, unless and if it is not given, you assume these values. Okay. Now, if I want to plot this same graph in per unit, how can I draw this same graph in per unit? Because you will get scared, right? I don't want you to get scared. So I will write here this actually is the external characteristics. Okay, so this is called as the external characteristics. Okay, so now uh, if I want to draw this in per unit, how will I draw it? So few things I have already mentioned to you, right? What have I mentioned to you? That my like V rated is EF. So that means what will be the per unit? Per unit will be divided. Everything, all the voltage levels will be divided by the rated, right? Actual upon rated is known as the per unit quantity. So everywhere I will divide by EF. So EF, this will be 1 PU. This will become 1 PU. This will be 1.41 PU, right? So actually should write PU here, otherwise you will get confused. 1 PU, 1.41, 4 PU, 2 PU. Okay, and yeah, this will be the value. So here what will be the case? So case, right, one thing is this will not be EF by XS, this will be 1 by XS basically. No, not 1 by XS, this will be EF by XS divided by I rated. I don't know what is the value of I rated, so I have to divide by I rated only. I don't know, it will be given to you in the question, right? 1 by I rated, that will convert this thing into per unit. Okay, and your 1 PU, as this value is higher than I rated, so your 1 PU, that is I rated PU, will be somewhere behind this here. Okay, so this will be 1 PU basically. This will be 1 PU. Okay, so please don't get scared if this graph is shown to you. Okay, it is the same graph, right? Just they have written everything in per unit, that's it. Okay, please don't get scared by this graph. Okay, now yeah, let's come to the next one, that is the internal characteristics, right? Internal characteristics is the one in which I will keep my VT constant, that is we are connecting it to a grid, power grid, right? So my VT will be constant. So this is known as the internal characteristics of synchronous generator. Okay, that's it. Okay, so yeah, so now what will happen? Now again VT is constant. So what is my EF? Basically I want to write my EF in terms of VT. So EF will be this VT angle 0 plus again plus JIA into XS. Okay, VT will be EF VT IA JXS, same thing, same I will repeat again. In no load what will happen? No load basically means IA is 0. If IA is 0, EF will be equals to VT. This was the case A. Okay, case B will be in 0 power factor, lead. Now in case of lead, what will be the current? 0 power factor current IA will be IA angle plus 90. So now my EF angle delta it will be in the same phase of VT only, but it will be VT minus IA excess, right? It will be negative. It will not be positive anymore. It will be negative. Basically, plus J into plus J is minus 1. Okay, minus IA. So this time, like, delta is 0. Okay, so there is no active power transfer. That's why the delta is 0. So that's what that is the significance of delta, right? What does 0 power factor means? 0 power factor means I am not supplying any power, active power. I am not supplying any active power. I am supplying only reactive power. So if I am not supplying any active power, what is my P? P is EF VT XS sin delta. So EF is non-zero, VT is non-zero, XS is non-zero, delta is 0, right? Sorry, P is 0 because I am not transferring any active power. EF is non-zero, VT is non-zero, XS is non-zero. So of course, sin delta has to be 0. That means delta has to be 0. Just give me a second. I'll drink a bit of water. Yeah, sorry for the interruption. So let's now start basically. So now, if it is at 0 power factor, what do you call lagging, right? For leading, if you see, it is reducing. So now how the graph will look? So now if I draw the graph, right, roughly I will draw the graph. This is my IA, this is my EF now. This is not my VT anymore, right? EF. And let's say at no load, when IA is 0, it is equals to VT. Okay. Now if I see the voltage is linearly reducing, so now it will reduce linearly and not increase. So now the short circuit current will happen due to the leading load, not due to the lagging load. Okay, so the bottom side will be now the leading load. Okay, so this will be 0 power factor leading. Am I correct here? Yes, I'm correct. 0 power factor leading. Okay, zero power factor, just hold on. 0 power factor lead. What will be the slope? The slope will be minus XS. Slope will be okay. Slope will be minus XS. Now let's plot for the 0 power factor leading case, right? 0 power factor, okay, sorry, lagging case. 0 power factor, this will be C. Lagging case. So 0 power factor lagging case, it will be IA, that will be equals to IA angle minus 90. Okay, so my what I can do, my EF angle delta this time will be what? VT. This will become minus 90. So minus J into minus J is what? Plus 1. So this will be plus. It will just be the opposite, right? Opposite. So it will be IA into XS. So the slope will be now positive. Okay. So this will be 0 power factor Again, no power is getting transferred. That's why the angle you see delta is 0. Okay, so 0 power factor, lag, and your slope will be what? XS. Same you can do. Okay, same again you can do for unity power factor. Now for unity power factor, we will draw the phasor. Okay, for unity power factor, what is the phasor? So I have this VT here, right? VT is fixed. This is my reference, and it is unity power factor. So my IA also will be in the same direction. What is my EF? EF, if you see, EF is equals to VT plus JIA XS. So I have to shift this by 90 degree and add with VT, right? Plus 90. So plus 90 means move this, rotate this in the anti-clockwise direction. So this will move here. Okay. So this will be J IAXS, and ultimately this VT plus this component will be my EF. So my EF will be here. Okay, this is my EF, and of course I can see there is some delta here, angle between the VT and EF. So obviously power will get transferred. So if I increase the VT is constant, right? VT is constant. If I keep on increasing my IA, what will happen? If I keep on increasing my IA, this will increase, right? This length will increase. So previously if VT was here, now EF has gone further, right? So if I keep on increasing my IA, EF will keep on increasing, and obviously the delta also will keep on increasing. Okay, why EF will keep on increasing? Because the length, right, is just a Pythagoras triangle, right? This square plus this square. Now this is fixed, this is increasing, so obviously the hypotenuse also will increase. Okay, delta will increase, the EF also will increase. Okay, so if I keep on increasing the load, this is increasing. Okay, this is increasing. Now what kind of curve will this follow? That I want to know. What kind of curve? So IA has angle 0, right? Because VT has angle 0. VT is equals to V angle 0. So IA is equals to I angle 0. Okay, so basically I can plot here EF is equals to V plus J IA XS, or the magnitude of E is basically V square plus IA XS, IA square X square whole square, right? So again it is what? It is kind of a hyperbola. Again it is a kind of hyperbola, or if I want to directly plot EF, it is under root, right? Under root will be somewhat like this. Square root will be somewhat like this. It will be something like this. Okay, this will be the plot. Sorry, not like this. This will be the plot. How can I say if the slope is increasing or decreasing? So like the graph, right? You can plot this. Okay, how can I say that will the slope, like there can be two ways, right? Either it can be, like I will say, either it can be like this, either it can be like this, or it can be like this. Now which one to choose? Which one to choose, right? Because it is non-linear, both are non-linear. But in this graph, it is, the slope is always reducing. Slope is always reducing. But here the slope is always increasing. So if I double differentiate and check the sign of the slope, like if I double differentiate this function, right, and then check the sign whether it is positive or negative, that will give me whether it is a monotonically increasing function or monotonically decreasing. So everything is important. So in mathematics, I have taught this in basics of calculus, right? So every single thing will be used. So if I see here, right, if I differentiate this, so this will be DEF with respect to what is the variable here? Variable is IA. So I will differentiate DEF by DIA. So this, right, this will be 1 by under root, this will be anyways a positive number, V square plus IA XS whole square. Okay, into half into 2 IA XS whole square. Okay, now I have to double differentiate it. If I double differentiate it, right, this denominator will be anyway squared, right? So this will be V square plus IA square. I'm just doing it in rough, right? You guys can also do it. Okay, I'm just doing it in rough. So 2 will anyways get cancelled. 2 will not be there. Okay, so in the numerator I have x square. X square is just a constant number. So now this differentiation of this into this, so this will be I'm just doing it in rough. V square plus IA square XS whole square minus, this will be IA into this number, right? Root V square plus IA square XS whole square. So when IA is 0, if IA is 0, right? If IA is 0, what do I observe? So initially for very low values of IA, this is gone. This is V square, this is gone, V square, V square. So it is something positive. If IA is 0, right? It is something positive. So initially the slope will increase. Okay. Now, after a certain point, will this dominate ever? Okay, 1 minus, okay. This is, okay. This will be, okay, I have to differentiate this as well, right? This I have to differentiate. Okay. This will be tough. This differentiation will be this only. Okay, 2 into IAXS. Okay, this is IA whole square. X is also, it's kind of tough. Okay, it's kind of tough to differentiate this, but I guess what will happen is some this number will be some positive number only because differentiating it. So I guess the graph will be somewhat like this. Initially it will be increasing because initially IA is 0. Initially it will be increasing, and then suddenly it will go towards 0. Okay, the slope will go towards, slope will reduce. The graph will be somewhat like this. Okay. Now let us find few key points. What is the key point? Key point is this one, right? This point. When my, at the short circuit current, when it is EF by XS. When it is EF by XS, again the same thing, right? My magnitude of EF at this load, EF by XS, is equals to 1.414 EF. Okay, at IA equals to EF by XS. The same thing, right? This will not change. This will be same. So again, it will be here 1.414 EF. Okay. Now can you do it? So this was for the unity power factor. Can you do it for the lagging and leading? Same, right? For lagging, it will be somewhere here. It will follow this. It will try to go to the 0 power factor lagging, and for leading, it will be somewhere around here. For leading, it is here. For lagging, it is here. Okay. So yeah, I hope you have understood this point. I hope you have understood this point. Okay, I hope you have understood this point. So these will be the plots for the what do you say, for the case 2. Okay, case 2, like I have drawn the phasor diagram properly. You can go through this, right? Same thing, whatever I have discussed, same thing is drawn here properly with written notes, so that you can understand later on. So this is the summary basically. Okay, and again, if you want to plot this in per unit, what you will do? Just simply you will do one thing. This will be divided by IA rated, 1 by IA rated, and somewhere here 1 pu will be here. Okay, and this, right, this will be like VT rated is the rated voltage. This will be 1 pu, this will be root 2, this will be 1 pu, and yeah, everything else is fine. Okay, and this right here, this will be 2 pu basically. Will it be 2 pu? I just want to confirm. So here, right, at this point, yeah, when it is lagging, so when my current is, okay, this time, right, okay, one small mistake I have made. This time it will not be EF by XS, sorry, it will be VT by XS actually. That I am extremely sorry about. Okay, yeah, sorry. When my EF is 0, right, so when IA is VT by XS, that's why you should not just do copy paste and mug up things, right? So this will be VT by XS. I'm really sorry. Okay, this will be VT by XS. So this time my short circuit current will be VT by XS. If my short circuit current is VT by XS, so if I put here Vt by xs, what will be the E value in this case for lagging load? EF for lagging load, it will be Vt plus Vt by xs. So Ia is Vt by xs, so it will be Vt again. So this will be 2 Vt. Okay, so this value will be here. EF will be equals to 2 Vt. Okay, that is the difference over here. So yeah, this will be Vt by xs. This will not be root 2 times here. Sorry, what I was doing, what I was thinking. I'm really sorry. This will be that's why you should not never just do copy paste. Okay, so here, right, in the graph, yeah, this will not be EF by xs. This will be Vt by xs. Okay, and yeah, this will be root 2 Vt. Here this will be 2 Vt. Okay, yeah, so yeah, this will be root 2, this will be 2. So this time my basically like rated voltage, EF rated for per unit is Vt, and my IA rated is some IA rated value, I don't know, but this much I know that IA rated will be somewhat lower than the short circuit current, that is for certain. So that's why this line is coming, rated current is coming before this. Okay, that much is certain. This will not be again EF by XS, this will be Vt by xs. Okay, this will be Vt by xs. So yeah, so this is the graph basically. I hope you have understood this basic point. Okay, so as I will go downwards, it will go from lagging to leading. Okay, so in case of lagging load here, what I am observing, the voltage actually EF, I have to provide more excitation. Does it intuitively makes sense? Does it intuitively makes sense? So let's try to understand it intuitively. Intuition. And this portion is the most important one, right? So if my load is lagging, what does it mean? Load lagging means it is demanding reactive power. It is demanding reactive power. What does reactive power actually means? Basically, it tells that I have to provide flux. Basically, reactive power is what? It is a power due to which I am able to generate magnetic field. So I have to generate magnetic field. Generate magnetic field. So if I have to generate magnetic field, how will I generate it? How will I generate magnetic field? So I will generate magnetic field by what? By providing flux. Someone has to supply flux. So flux is required. Flux is required. Who will deliver it? Generator. Generator will deliver. How can I deliver flux? By overexciting the generator. So I will overexcite the generator. That means what? EF will be higher than the Vt, because if I increase my excitation, right, IF, if I increase, EF will increase, and if I increase IF, more flux I will be able to deliver, because remember this, right? What was the thing? EF is equals to root 2 pi f phi n. Okay, so the more EF I increase, that is more IF I will increase, EF will increase, hence the flux will increase, keeping everything else constant, right? So yes, intuitively it does make sense that if the load is more lagging, I have to increase my excitation, right? So the conclusion is, already we have discussed this actually, if load is lagging, I have to provide more excitation to get the uh, same value of IA. So if we see in the same, like if I see in this along this line, right, IA is constant here. In this line, IA is constant. So I see for lagging load, I have to provide more excitation. For leading load, I have to provide less excitation. For leading load, I have to provide less excitation. For lagging load, I have to provide more excitation. That does make sense intuitively. Trust me, this analysis, intuition, no other educator in GATE field anywhere else, right? In any paid content, no one will give you, no one will tell you this, all this, right? No one will tell you. Okay, they just write down the equation, that's it. Okay, they don't tell you the intuition behind it. Okay, trust me. In PrepFusion, you are learning the concept, obviously problem solving ability, and the intuition, why it is happening. Everything I'm trying to explain very clearly. Okay, now I will give you a homework. Okay, this is a task for you. The task for you is do the same, analysis. Like, I will not do it, okay, because I want you to figure out by yourself. Everything I will not do. Do the same analysis for synchronous motor and put it here. Okay, for synchronous motor, what analysis? Two cases we did, right? We did two cases. So one was the internal characteristics, internal characteristics, and external characteristics. Okay, so one will be the internal characteristics, another one will be the external characteristics. So I hope you have understood. Like so this will you will plot with VT versus IA, and this will plot with EF versus I. Okay, and what you'll do is you will basically you will just see it is just opposite. Okay, I will draw the circuit diagram for you. So for this, right, what will be the circuit diagram? Circuit diagram will be, this time VT will be here, right? VT will be leading actually, and your delta will be negative. Why? Because power it is receiving, not delivering. The formula is P EF VT by XS sin delta. So if it is negative power, that means what? It is not delivering, receiving. That is correct, right? Delta should be negative here because it is a motor. It should receive active power, right? Not deliver. I mean deliver. It will deliver to the mechanical load, but from an electrical standpoint, circuit point, I am delivering the power, right, from electrical circuit. So here the motor will be there. Okay, what will be the equation here? Equation will be Vt will be equals to, so if I am plotting the characteristics, it will just get flipped. It will just get flipped. All the graphs will be flipped. That's it. So EF will be here. EF angle. This will be EF angle minus delta. So EF angle minus delta will be Vt Vt angle 0 minus J IA XS. Okay, this will be the equation. Okay, and here, right, what will be the circuit here? Here the circuit will be same only. Basically, I will have a Vt, right, and this is the E. So this is my Vt. Vt can vary this time. This is not an infinite bus. and this is my jxs. So here the equation will be, it will just be opposite. So here Vt will be equals to Ef angle minus delta, this will be Ef angle minus delta plus J Ia xs. So basically you will plot the graph, homework, and the answer will be, answer to all of this will be basically opposite of generator. I want you to think a bit, okay? So now let's come back to the next topic. Before this, one more conclusion. Okay, I cannot get this right. One more conclusion I want to give, right? Okay, I cannot say. Okay, just give me 1 second. Give me 1 second. Let me get this here. This will not come here. Get this here. Get this here. Get this. Yeah. So let us now discuss about the same external characteristics, and if I want to determine the, not the external, sorry, let us go through the internal characteristics, and if I want to determine the power factor. So if I want to determine the operating power factor, so if the power factor is given to me, then I can discuss about the excitation. Now let's say power factor is not given to me. Let's say if the power factor, if the power factor is not given to me, then how can I solve it? Okay, so let me draw the phasor for different power factors, and then I will discuss how can I actually derive the expression. Okay, so let us first discuss about alternator. So for alternator, what do I know? For alternator, this is my circuit diagram, right? Generator will deliver E angle delta, EF angle delta to the infinite bus. So mainly we will be discussing by default about infinite bus. So we generally avoid the case 1. Mostly we discuss about case 2 only, because that is the most practical case, right? We will connect our generator in a infinite bus. Okay, yeah. One more thing I forgot to tell you is that if you observe here, right, for the isolated case, if my load is very lagging, then the voltage decreases drastically. The terminal voltage decreases drastically. Can you think of example where this can be a problem? So I will say you that observation, right? In case of the case 1 I'm talking, I forgot to mention it. So observation at high lagging loads terminal voltage Vt reduces drastically. So is it a problem? Yes. I will give you a practical scenario in weddings, right? In weddings. So what we do, we have our generators, right? External generators. Weddings or any function, let's say any function, family function you are having. So you will have external generators there, right? And those generators you connect just for backup power supply, because let's say the current is gone. Obviously you don't want your function event to be interrupted, function or event, right? So in those kind of cases, right, you will see, you will observe whoever are the organizers, they will make sure that the number of fans or any kind of load that requires that is lagging load is less, right? So they don't care if it is leading load. For leading load, they don't have a problem. But if very high number of lagging loads are connected, then the voltage drop will be drastic. So they don't want lagging load, like of 1-2 lagging loads is fine, like 5 fans, 10 fans is fine. But if 50 fans, like, or 20 fans are connected, right, then the voltage drop will be significant and the motor will not work at all. Basically, voltage will be gone down to zero and no power. Okay, zero power. So yeah, this is a interview question. Why we do not want lagging loads? Okay, in an isolated system. So this is the answer to the question why we do not want lagging loads in isolated system. Okay, so I'm preparing you for both interviews, everything, right? Okay, so yeah, that was one quick answer. So now let's come back to this. Right here we are discussing alternator. So this is my VT, correct? Angle 0. Again, if I write, draw the phasor diagram. Okay, let me draw the phasor diagram for unity power factor. For unity power factor, this is my VT. Okay, VT, IA will be in the same phase. And what is the equation? Equation is the same old equation. EF angle delta will be equals to VT plus J IA XS. Okay, so JIA XS, so JIA XS will be somewhere here. This is my IA XS and this will be my EF, correct? So this is delta, power angle between the EF and VT. So one thing I want to understand, that if it is a okay, well, I want to add the synchronous impedance as well, because I want to actually fully derive it. So let me, sorry, not synchronous yes, I mean the armature resistance, right? So this time, right, I will write my this, right, I will not just put the inductance here, I will put a box ZS will be RA plus JXS, because this is important, so I will not do approximations. So even if you do approximations, what you will do, you will make RA 0, okay? So this will be RA plus J, sorry, this will not be J anymore, this will be plus IA into ZS, that is RA plus JXS. So now it will be VT IARA plus JIA XS. So first of all, I have to add IARA in the same direction. So I have to add IARA. So IARA will be somewhere around here, right, in the same direction. Okay. Then I have to rotate my JXS by 90 degree. This will be rotated. Okay. EF delta okay. So now yeah, Now I want to clarify this. So this distance is how much? This distance is IA into RA. So now if I take the projection of EF along this axis, right? So from this I can simply write that EF cos delta will be equals to this vector sum VT plus IRA, right? Along the projection. So VT plus IRA. So we got a very important conclusion that if EF cos delta is equals to VT plus IRA, then it is operating at unity power factor. Okay, do you need to remember it? No. Draw the phasor diagram. It will take you 30 seconds. So remembering this is difficult. For me as well, it is difficult. I will draw the phasor diagram. Okay, I will draw the phasor diagram. So very important conclusion. Now what about, sir, what about for lagging and leading loads? So we will come to that. We will come to that. Okay. So let me draw the phasor diagram for a lagging load. If I draw the phasor diagram for a lagging load, okay, lagging power factor. Okay, for a lagging power factor, how will the phasor diagram be? So again, this will be Vt. Now if the current is lagging, that means current will be somewhere around here, correct? Current will be here. This will be Ia, this will be theta. So now, right, now what is my EF? EF is again the same thing, right? It is Vt plus IaRa plus J IaXS. So IaRa, right? Remember Ia is not in the same direction. So IaRa will be somewhat here. This will be IaRa. IaRa. What about JXS? So JIaXS will be 90-degree clockwise, right? JIaXS will be 90-degree clockwise here. Somewhere here. Okay, I'm just drawing the rough diagram here. So what will be my EF basically? So my EF will be this two connections, right? Okay, I will try to make it straight line. Yeah. So this will be EF, and remember this delta. This is delta. Okay, this is delta. So now how will you draw this? So how will I now make this projection? What is EF cos delta now? What is EF cos delta? So EF cos delta. So this is delta. Okay, and this is theta. If this is theta, that means this angle also will be theta. Correct? This angle also will be theta. This is theta, this is theta. They are both parallel. This is a straight line. So it will be also theta. Okay. This is theta. And what I can comment is if I draw a straight line over here. Okay. So if this is theta and this, right, will be 90. Correct? It is just a triangle. This is a straight line. This is a straight line. So it is 90. So this will be what? This will be 90 minus theta. If this is 90 minus theta, this will be what? So this whole thing is 90, right? Because it was JIXA. So this is 90 minus theta. Correct? This is 90 minus theta. 90 minus theta. So and this whole angle is 90. So this is what? This is theta. This will be theta. Okay. Now can you write the projection? Right? So this length, right? This length is IAXS. This length is IRA. So now can I draw the projection? So projection along this axis. I want to draw the projection along this axis. So first is EF cos delta along this axis. That is EF cos delta. What about the other parts? So it is VT. VT will be along the axis only. So it will be VT. Okay. It is VT. Now again IRA cos theta. IRA cos theta. Okay. IRA cos theta will be along this axis. So it will be plus IRA cos theta. Okay, what about this one? So this is IA XS cos theta, but I don't want this. I actually want this one, this component. So this will be IAXS cos theta. This will be, sorry, sin theta. This is cos, this is cos, basically this will be sin theta, right? So this will be plus IAXS sin theta. Okay, so basically what I can comment, you can comment that if I neglect this, right, if I neglect this excess, right, or you don't neglect the excess, like if this excess is present, so what I am talking, if you remember this component, what was this? This was present somewhere, right? This was present here, Vt IRA, and cos theta was there, but it was unity power factor, so you could not observe it. So basically what they're telling you is, if my EF cos delta is greater than Vt plus IARA cos theta, that means it is a lagging load. For certain, you can comment that it will be lagging load. Again, do you need to remember it? No. Draw the phasor diagram. Okay. How? Because EF cos delta is higher, right? Because I'm adding something. All these are lengths, positive quantities. So I'm adding something, right? So it will be higher than this value. With this value, I'm adding this to get this, right? So EF cos delta has to be higher than this value. So same conclusion, homework task for you is the other one. So if my EF cos delta, same homework task for you, is less than Vt plus IRA cos theta, the power factor will be leading power factor, because they will just give you the value of cos theta, right? You don't know whether it is a lagging or leading load. This is how you identify whether it is a lagging or leading load. Okay, if your RA is 0, directly you compare with cos delta, EF cos delta, right? Okay, no need to remember it. RA 0 simplifies your calculation even further. Okay, RA equal to 0 simplifies your calculation even further. You just directly compare with Vt. Okay, directly with the terminal voltage. So if your terminal voltage is less than EF cos delta, then the load will be lagging. If your terminal voltage is greater than the EF cos delta, load will be leading. Does it make sense? Yes, it does make sense, right? Because Vt has to be higher. So like this, you can remember that for leading loads, generally what happens, the terminal voltage is higher. For same excitation, the terminal voltage is higher. So how can you remember? So we can remember it like this, that for leading load provided with same excitation, terminal voltage will be higher. Okay, please don't get confused by this graph. I know you will get confused by this graph. You will say, sir, here you are saying leading load voltage is going low here, sir. Sir, there you are saying high. What is this? What is this? Is this Vt? Is this Vt? No, right? This is EF. So I am saying I require less excitation to provide the same terminal voltage, right? So just this, it is saying same thing only. Here also I am saying the same thing. Okay, please repeat, understand. Here I am saying I require less amount of excitation to provide same terminal voltage. Here I am saying if the excitation is same, then terminal voltage will be higher in the leading load. Okay, rewind, re-listen to it to me. I hope you will get the point. Okay, same thing, whatever I've discussed, same thing is written over here. How the graphs will look, everything will look. I've already drawn the I've already drawn the phasor. I have not drawn the here I have drawn the phasor diagram, but I'm not doing it. Okay, I have to do it again. Okay, anyways, I have done it, right? So I think, yeah, this we don't need to draw. This you can, I hope you can understand, like how this is IA, right? I forgot to write this IA. IA should be here. Yeah. So basically the phasor diagrams will be, so here, right, the phasor diagram, I will draw the phasor diagram real quick. So the phasor diagram will be something like this. It will be IRA, it will be IRA and this will be IA XS. Okay, so this will be my EF delta EF, and same equation, right? Same equation, that my EF cos delta will be equals to VT plus IRA. That's it. Okay, for unity power factor. For non-unity power factor, like you can draw, you can draw the graph. I have to again draw the graph. That is like unfortunate. So here, right, this will be IRA. Okay, and 90-degree phase apart will be my IA JXS. So this will be IRA IXS. Okay, EF. Okay, so in this case again same thing, right? Same thing we will do. This will be delta. So if you do this analysis, you will get this value. Okay, that I derived. Okay, for the other one, right, for the, this is for what? So lagging, yeah. For leading load, what you will see, it will come out to be negative. For leading, it will come out to be negative. Why it will come out to be negative? Sorry, for lagging it will come out, so yeah, for leading it will come out to be negative. Why it will come out to be negative, I will show you. So that's why it will be the less than condition. So this will be IRA is in the same direction, and I have to flip this by 90. So yeah, you are observing, right, it is basically going downwards. It is going downwards. So now what will happen is, this will be my EF, this will be my EF, this will be my delta, this will be my IAXS, this will be my IARA. So you are observing, if this is theta, this also will be theta. Now if this is theta, right, if this is theta, this will be theta. If this is theta, this will be theta. If this is theta, this will be 90 minus theta. Okay, now I have to find out the projection, right? So EF cos delta, simple trigonometry I am doing, EF cos delta equals to, this value is going upwards, IRA. So VT is going upwards, IRA also, IRA cos theta, right? IRA cos theta, because I have to take the projection along the reference. So VT plus IRA cos theta. Now what about this one? So if you see this, right, if I take the projection along, like this is just if I take the projection along this axis, it is just parallel to this, so it is along the reference, but in opposite direction. So it will be IAXA cos of 90 minus theta, that is sin theta, but in opposite. That's why I have to add a negative sign, minus IAXA sin theta. Okay, so here if you see, I'm subtracting something from this value. That basically means that my EF cos delta will be lower than Vt plus IRA in case of a cos theta, in case of a leading load. Or you can directly write that my EF cos delta will be lower than Vt. Okay, so I hope you have understood this. Now for motor, just the opposite. For motor, just the opposite. You draw the phasor diagram, you will see, you will get the results. You will just arrive to opposite. So remember for generator, for motor, you just keep it opposite. Just keep it opposite. So in case of a unity power factor, that's why we call it as nominal excitation, because the IF required is nominal. IF required is nominal. Okay. Here for a lagging power factor load, what can I call it? For a lagging load, I have to do over excitation, because my EF, I have to provide more excitation to get the same voltage. So if my EF cos delta is greater than Vt plus IRA cos theta, also you can comment about the excitation. You can also comment about the excitation, because it is lagging load, of course it will be over excited, right? So IRA cos theta, so this will be over excitation. Okay. In case of leading load, it is under excitation. Intuitively also it makes sense, right? The condition for under excitation is this one. Okay. I hope you have understood, and here it will just be opposite. It will just be opposite. For lagging load, it will be under excited. So for lagging load, it will be under excited. For leading load, it will be over excited. Okay. So just remember, for generator, for motor, automatically everything will be sorted. Okay. So let's do a very basic question. Okay, you can pause the video and try this question out by yourself, and I will come back with the solution. Let's solve this question. So whenever questions something like this comes, right, always try to draw the circuit diagram. Okay, so an alternator having a synchronous reactance XS is 0.8 pu. So everything is given in pu, per unit. So everything I will write in per unit only. So it is a synchronous, it is a alternator having synchronous reactance, this connected to a infinite bus. So I will draw the circuit diagram. So the circuit diagram will be this. Circuit diagram will be this. So this is my Vt, okay, and this is my EF angle. Delta, right? EF angle delta. This is my, like, synchronous reactance is given, and they have told me to neglect losses. Losses meaning RA is 0. Whenever they say neglect losses, that means RA is 0, iron loss, all those things are 0. So I have only this J 0.8 pu, this synchronous reactance. Okay, and Vt will be what? 1 pu. Okay, always Vt will be 1 pu. In per unit, Vt is at rated voltage, so it is 1 pu. Okay, so if it is in per unit, okay, it will always be 1. Now they're telling me its excitation EMF is set to 1.3 pu. So I know what is the magnitude of excitation EMF, that is 1.3 pu, that they have given to me. Now what they are asking, also it is telling me that it supplies an active power of 0.5 pu. So the power delivered is 0.5 pu. Okay. Determine the load angle per unit armature current and power factor. Right? How will I determine the load angle? So the load angle is very simple, right? Just write the equation. So what is the equation of power? So in absolute quantity, we derive the equation of power EF Vt by XS sine delta. Okay, can I write this same expression in per unit quantity? How will I write this same expression in per unit quantity? So I will just divide by this P rated. Okay, I will just divide by P rated. So everything here will be converted to per unit quantity, right? I hope you are understanding, right? I just want to write this in per unit. So this is already in per unit, right? This does not have any like quantity unit. This does not. This is unitless. So whichever quantities are unitless, those are already in per unit. So this I have to write in per unit. That is given to you 1.3. This I have to write in per unit. That I know is 1. This I have to write in per unit. That means it is basically so if everything is per unit, then the power also will be in per unit. Okay, so which is 0.8, right, and this is 1.3. So from here I can simply find out the load angle. Load angle is very simple because power in per unit is 0.5, which is equals to EF, which is 1.3, into VT, that is 1, divided by XS. What is XS? XS is basically 0.8, right, and sine delta. So from here I can easily find out what is my sine delta. From here I can easily find out what is my delta. So 0.8 into 0.5 divided by 1.3 sine inverse. So sorry, delta will be 17.92 degrees. So first part is over. Now they are asking me what is the armature current. How will I find out the armature per unit armature current? So again same equation, right? Same equation. What is the equation? So EF angle delta EF angle delta is equals to VT plus IA JIA into XS. So from here I can easily find out my IA, right? So if I write everything in per unit, then IA also will come out to be in per unit. So IA will be EF angle delta. So EF is 1.3, angle delta is 17.92 degrees, minus VT is 1 angle 0, divided by J into 0.8. J into 0.8. Okay, so from here I can easily find out the IA current. So what I will do, first I will write this numerator in polar format. So this will be cos of into this 1.3 minus 1. So this will be 0.237 and then plus this 1.3 into 17.92, sorry, sine of 17.92, which is I guess into 1.3, which is J4, divided by this J.8. I will write this in polar. So this whole square plus 0.237 whole square whole under root. So 0. 0.465 and the angle, right, angle I have to find out, 0.4 divided by 0.237, so tan inverse of this, so it is 59.35, and in the bottom I have 0.8 angle 90, right? So actually the angle will be minus 90. So actually the angle of the current, right, IF phasor quantity, angle of the current is minus 30.64, so it is lagging current, 30.647 degrees, and the value of the current is in per unit is 465 divided by 0.8, so this is 0. 58 125, okay, 0.58125. So this is the current. So we have got the, what is the power factor? So power factor will be cos of this, right? Cos of minus 30. So cos of minus 30.647, cos of this will be 0.86, lagging. Okay, so this is the power factor basically. So I hope you have understood this basic point. Now first part is over, okay, part A is over. Now in the second part they are asking me if the alternator excitation is changed, if the alternator excitation is changed such that the active power output and the armature current remains same, okay. So IA is same and power is also same. Calculate the new excitation EMF, the apparent power and the corresponding power factor. So what is power actually equals to per unit power? Power is VIA into cos phi. VT is so VT is constant. VT is always constant. And question, in the question they have given me that IA is constant, and your power is also, they have told me that power is constant, same power output, right? Power is constant. So pause the video and tell me, will the power factor be constant or not? Be truthful to yourself. Pause the video and tell me, will the power factor be constant or not? Will it be constant or not? Be truthful, okay? So here, right, if your answer was it is constant, you are wrong. If you said it is not constant, then also you are wrong. Actually it is partially constant. Basically the magnitude of the power factor will be same, cos phi because here, right, we don't factor in the behavior whether lagging or leading, we just discuss about the magnitude. So magnitude will be constant, but previously if it was lagging, now it will be leading. Why it will be leading? Because they are telling me that I am changing the excitation, and if I change the excitation, then I can change the power factor. If I change the excitation, I can change the power factor. Can you see here? For the same terminal voltage, here, VT, right? If I change the excitation, if I go from leading to lagging, the basically if I change the excitation, right, the basically excitation changes, power factor change, or power factor changes, excitation change, right? Both way works. So yes, power factor will change, magnitude will not change, but from lagging it will go to leading. Trust me, this is a very famous question, and you will see everywhere else they will solve this with so much complexity, Trust me, you go anywhere else, you will see this question has been solved with so much complexity, but this question is actually very simple, okay. So power factor will now change to leading, but the magnitude will remain same. So still the power factor will be what? 0.86 in the second part, 0.86 lead. Lead, okay. Still the power factor will be 0.86 lead, okay. Power factor I already know. So other things are remaining. What is EF? What will be the value of EF? They are asking me. and what will be the new armature current, right? All these things they are asking me. So what will be the new excitation, armature, so armature current is same, what will be the new excitation? So if armature current is same, what will be the armature current? Armature current magnitude is same, right? Magnitude is 0.58127. So this will be same, but power factor will change. So instead of it becoming minus 30, it will be plus 30 now. It will be plus 30 because it is leading now. Okay. I will put this value in the same equation. What equation? From here I can easily find out my EF, right? What will be EF? EF will be simply VT plus J IA XS. Okay. So this will be EF will be EF will be equals to 1 angle 0. This will be constant. IA J is 1 angle 90, right? And IA is 0.58125 angle plus 30. So from here you can both find out the delta angle and the EF. So trust me, like other, you will see anywhere else, any other platform, right? They will solve this with so much complexity. Trust me, I'm not even joking. I'm not even joking. Okay. So this is point. Okay, this will be 120, right? So 120.647 into 0.58125. So this will be negative and plus 1. So 0.7 minus sorry, yeah, if I do sine of this, right, sine of 120.647 sine, so 0.866 into, this will be same only, this will be into 1 into 0.58125. So this will be plus j 0.5. So this whole square plus 0.7 whole square whole under root, so 0.86 angle, okay, 0.5 divided by 0.7 tan inverse. So this will be 35.54. So the new power angle delta will be 35.54, and uh, excitation your excitation will be what do you call, sorry, your excitation will be 0.86. Okay, this will be the new delta angle. So previously what was the delta? If I see previously delta was 17.2. I will just quickly check whether I am doing everything correctly. Okay, just quickly once again verify it whether I am doing everything correctly, because according to me the delta should come out to be something else. Okay, just give me 1 second. So this is 30, this is 30, right? 30 point, yeah, 30.6, 120 plus 30.647 cos of this plus 1. Okay, sorry, 120.647 cos of this plus 1. Okay, now it is coming out something else. Oh, sorry, 120.647 cos of this into 0.58125. It is 58125, right? IA should not change. IA magnitude will be same, plus 1. It is coming out to be, no, 703 only. So 704 whole square plus 0.5 whole square, okay, whole under root 0.862327. I will just check whether this is also correct. 0.58125, sorry, sine of 120.647 into 0.125. Okay, yeah, it is correct only. So I guess this is correct only. 0.704 tan inverse, yeah, 35.34. I guess something, maybe I would have messed something up. So this comes out to be 35.54. Okay, so hold on a second. This armature current is somewhat dropping because previously I calculated the armature current. No, it is correct only. Yeah, this is correct only. Armature current is same only. Yeah, it is correct only. Yeah. So yeah, it is correct only. So armature current remains the same, active power and the armature current remains the same. Yeah. So everything is set. So now they are asking also the apparent power. What will be the apparent power? So apparent power, right, in per unit. Apparent power in per unit. So this is the excitation. Excitation is delta, like magnitude of EF we have already found out. That is 0.8623. Delta we know 35.54. And yeah, one small mistake I had done. This, right, is not 1, right? 1 angle 0. It is 0.8. I forgot. It is excess. Excess is 0.8. This is 1 angle 0, but I forgot to write the excess here, right? So 0.8 should be there actually. Sorry. That is my mess up. So that's why I calculated a different value. So 0.51125 into 0.8, that is 0.467, right? This value is, this multiplication is 0.46. So 0.465. So 0.465, and now I will do the this, right, cos of 120.647, cos of this into 0.465 plus 1. So this, right, comes out to be 7.763 actually. My bad. This will come out to be 763, and this, right, 0.465 into 120.647 sine of this, right, comes out to be 0.4. This will be 0.4. So this, right, divided by 0.763 tan inverse, this will be 27.67 degrees. Okay, and 0.4 whole square plus 0.763 whole square whole under root, this will be 0.615. Now it is fine. 27.67. Now again, these are the answers. Another thing they are asking, the apparent power. So apparent power for, like, apparent power for the what do you say, for the, this will be fixed, right? Apparent power for the load is fixed because IA is fixed, everything is fixed. Most cases they are asking the apparent power for the generator. For the generator, what will be the apparent power? It will be simply input to the generator, apparent power input to the generator will be simply EF into IA, right, in per unit. So EF is how much? 0.868615, and IA is how much? IA is 0.58125. Okay, so if I multiply these two values into 0.58125, so it is 0.5, almost approximately it is 0.5. Now does it intuitively make sense? It kind of makes sense. Why? You're saying this apparent power is almost approximately equals to the active power that the load is getting, because whatever reactive power is supplied by the load. Why? Because load is operating at leading power factor, hence load can supply the reactive power. So trust me, this intuition, all these things, no one and nowhere else you will get. Okay, so please लाइक ठोक दो, ठीक है, थोड़ा सा कमेंट वमेंट कर दो, अच्छा लगता है, मार्केटिंग करते रहना चाहिए. सो प्लीज़, like it will help us really out if you appreciate the videos, if you go into the first video of the playlist and comment there, really it will help us out. Okay, so yeah, that's it basically for this lecture. I hope you have enjoyed this lecture. I will see you in the next lecture with very important topic, that is V curves. Okay, that is the most important topic. So everything is from basics, right? I did everything from basics, no formula, nothing. Okay, so yeah, we will see you in the next lecture. Until then, happy learning.